Welcome back to Intermediate Algebra. Today we're looking at section 4.3, applications, otherwise known as story problems. So I know that story problems are really not anybody's favorite thing. And yeah, there's just really no getting around that. So I understand that. I'm going to try and make this as painless as possible. I have some steps here for you to kind of try and follow through. And I'm going to do two examples for you. But just really take your time, really dig in here, and try to make sure that you can do these. I understand that these really aren't anybody's favorite thing, but here we go. Let's take a look. So on this board, I actually have the steps that we're going to use for solving story problems. Now, unfortunately, it gets a little bit murky in the middle, but we'll take a look at that, and I'll talk about them when we do the examples too. So step one, I have written on the board here, read. Basically what that means is just make sure you read the problem. What is it that you're trying to find? That's always a really good question to ask because sometimes you forget about that question and you don't actually answer the question that you're being asked. So pay attention and read the problem. Step two, assign variables to everything you don't know. Okay, so in these problems, you're looking at 2 and maybe even 3 things that you don't know. Give them each a letter. They can be letters that have meaning. So for instance, if you have 3 people, you could use a letter for each of their names. Or you could just use X, Y, and Z if you prefer. But make sure you know what your variable represents because otherwise you get a little confused later on. Step 3, write equations. A couple of things here. They should be equal to the number of variables that you have. Okay, so we've done systems of equations. And when we had 2 variables, we had 2 equations. When we had 3 variables, we needed 3 equations. And that's going to hold true here as well. So, you just finished assigning variables. That's going to tell you how many equations you're looking for. If you've got 3 variables and only 2 equations, you need to find one more equation. My other point here under equations is to look at the totals. Okay, it can be a total amount of money, total distance traveled, all sorts of possibilities. But look for totals because frequently that's going to help you set up those equations. Step 4, once you have your system, now you get to solve it. If you get through the equations, the rest of it is really fairly straightforward. That's the hard part, okay? The equations, if you get those, you're going to get there. So solve your system. Once you've solved the system, make sure you actually answer the question that's being asked. Sometimes we find one answer and we needed 2. So make sure you answer the question that's asked. And last but not least, step 6, do a gut check. Does your answer actually make sense? So case in point, if you are trying to find the height of a tree or something like that and you get a negative number, probably not. If you're trying to find the number of people attending the movies and you get that 7.5 people are going to the movies, probably not. If you do that and you put it on my test, I will laugh at you because I'm sorry, but that's just funny. But do a gut check. Just say, hey, does my answer seem reasonable? Or did I lose a negative sign or something along the way that really messed this up? And now I've got something really goofy. So anyway, do a gut check. So there you go. There's our steps. I would recommend if you didn't do it the first time through, go back through this and write those down. They will be handy as we get into the examples. And again, I'm going to be doing 2 examples here, and we'll see those here in just a minute. Okay, here's our first example. So feel free to pause this and write stuff down or back up to go through it more than once and really figure out what's going on here. So this one is a pretty typical little chemistry problem. We're going to be mixing things together to create something else. All right, so here's the problem. How many ounces, I should say gallons, hold on just a second. Let's change that. How many gallons of 30% acid solution and 80% acid solution must be mixed to get 10 gallons of 50% solution? So, I read the problem. I know I need the number of gallons of each of these 2 solutions. So you'll notice that I assigned the variables x to be the gallons of 30% solution and y to be the gallons of 80% solution. You can further see that I have the answer here already, but we'll get to how I found that in just a second. So right away, I'm just starting by saying, what do I want to know? I want to know how many gallons of each of these things. There's my variables. Okay, so that's a great place to start. So before we go any further, we can ask ourselves this question. how many equations should I even be looking for? Well, I have two variables, so I should be looking for two equations. Remember, it will always match. Okay, the number of variables, the number of equations will always match. All right, so x and y, I'm looking for two equations. So what are those equations? Well, if you remember in the notes that I gave here just a few minutes ago, I said look for the totals. And so there are two totals in this problem. One is easy to see, the other one's hiding just a little bit. So let's start with that one that's easy to see. We need 10 gallons. That is a total amount of the mixture. So my first equation is just based on that 10 gallons. I know that these two things, when mixed together, when combined, have to equal 10. So x plus y is equal to 10. Gallons of 30% plus gallons of 80% has to equal 10. There we go. All right, next up, where's the other total? That's a little bit trickier one. All right, it's actually hiding in the amount of acid that we have here. So we need to end up with a 50% solution. And so anytime you have one of these mixture problems, you're going to have this second equation that's based on all these percentages. And so my advice is to just kind of get used to this equation, because it's going to look really similar every time you do one of these problems. So here's the thing. The total amount of acid is 50% times the 10 gallons. 0.50 times 10, or 5. Now, where are those gallons of acid coming from? They're coming from the 30% and from the 80% solution. So we're going to use those percentages over here. 30% times the number of gallons of 30% plus 80%, 0.80 times the number of gallons of the 80% solution. And when we add those two things together, we should get that 5. Okay, so again, go back through that. We're looking, the total here is the total amount of acid. 50% of that 10, half is 5. And it comes from those two places, 30% times x and 80% times y. So now what I notice is I have two equations, and you'll see I've got a third one here getting there. So I have two equations, x plus y equals 10, and 0.30x plus 0.80y is equal to 5. So I notice that I can do elimination on this. If I chose to multiply the first equation by negative 0.3, so I'll write that down now. I didn't have that there at first, but let's write that down, times negative 0.30. Right, if I multiply everything by negative 0.30, my x's are going to cancel. So I get negative 0.30x minus 0.30y, and don't forget to do the 10. Negative 0.30 times 10 is negative 3. Now my two equations have opposites for x, so I add, the x's go away. 0.80 and negative 0.30 gives me 0.5y. 5 and negative 3 is 2. We divide both sides by 0.5 and we get y is 4. So I need 4 gallons of the 80% solution. Well, we needed 10 gallons total, so what's left? The 6 gallons from the x. And sure enough, if you were to take that 4 and plug it in up here, if you solve, you get 6, and I get, so that makes sense. It's what we would expect. Did we answer the question? Yes. We have the amount of both acid mixtures that we need. And does it seem like a reasonable answer? I think so. We didn't get any negatives, so that's a pretty good start. It certainly seems reasonable. Neither one is bigger than 10. That would be bad. So it looks like a good answer. All right, let's do one more example. Okay, so for my second example, we're going to do a distance problem. We've got a boat going up and down a river. So here we go. A boat on a river travels 20 miles downstream in 2 hours. It takes the same boat 6 hours to travel 12 miles upstream. What are the speed of the boat and the current? So we want to find out how fast the boat is going and how fast the current is going. Because here's the thing, if you've ever canoed down a river, you can just sit there. You don't have to do really any work. You can just let the river push you downstream. But if you were to turn around and try and go upstream, that would be a lot of work, because then you're working against the current. And so that's kind of how we're going to approach this one. When you go with the current, it's going to help speed you up, basically. When you go against the current, it's going to slow you down. So let's take a look at what this is going to be. So I called B the speed of the boat and C the speed of the current. I like to pick letters that are not just X and Y. I know I used X and Y in the last one, but we just had percentage solutions. So anyway, but B for the boat, C for the current. And you can see I drew a nice little picture of a boat here. Congratulations, you don't get a whole lot of artwork out of me. But what we're going to work with here is the distance formula. Because what we have here is two total distances that this boat travels, right? It travels 20 miles downstream and 12 miles upstream. So the distance formula is that distance is equal to rate multiplied by time. Our rate, that's the speed. So that's going to be boat and current. That's really what we're looking for. So here are my two equations. Please ignore that times 3 out there for just a second. Going downstream, the speeds are working together, right? The boat and the current are both pushing in the same direction. So you'll notice that my distance is equal to two things added together. Is equal to the distance that comes from the speed of the boat, 2 hours times its speed, right? Because it's for downstream for 2 hours, plus 2 hours times the speed of the current, right? These two things are going to work together and get more distance than you would in just still water. The second equation for going back upstream says that the distance is 12 miles, but now since they're working against each other, you'll notice we put a minus sign in between. So the boat's doing a lot of work, and the current is pushing back. So the current gets the minus sign here because it's working against the direction of movement. And so it says it takes 6 hours. So notice we have the same sort of setup. The distance is equal to the amount of time, 6 hours, times the speed. But we do have the minus sign, and then the amount of time times the amount of speed. So going downstream, we get a plus sign. Going upstream, we get a minus sign. And now we have our two equations. So I multiplied the first equation by 3 because it's going to allow me to get rid of my c's. So when I did that, 20 times 3 is 60, 2 times 3 is 6, 2 times 3 is 6. And so now I'm adding these two equations together. So 12 and 60 makes 72, 6 and 6 makes 12, and the c's are gone. Divide both sides by 12, and we get that the speed of the boat is 6 miles per hour. So let's go ahead and write that up top. And then I plugged that 6 in, and I put it into this first equation, the 20 equals 2b plus 2c. So I plugged in the 6. 2 times 6 is 12, so I subtracted 12. Again, I'm running out of space here, so I didn't show all of my work. I know, shame on me. You should do that. Show your work, because you should hopefully have space. I'm running out. So 2 times 6 is 12. I subtract 12, that gives me the 8. Divide by 2, and c is then 4 miles per hour. And there we go. So, very fun. This is our second example. I know story problems are nobody's favorite thing. So, give it a shot. And if you have questions, especially, if you're in one of my classes, feel free to, contact me and we'll try and get those sorted. So, anyway, yeah, good luck. Have a great day.